That's hard work.
It was cheap.
Right.
That's all right, but y'all are working it.
We're fine.
You deserve it. So, this is Dr. Faris, winner of the Middleton Award. I'd like to know if you could give us a few words on what brought you to that award and the research that you did.
Well, we've had a long-standing interest in trying to understand how insulin works normally and why it doesn't work well in type 2 diabetes and obesity. And of course, we've identified through the years a number of the factors that are important for as to how insulin works intracellularly after it binds to its receptor. It has to do certain things to control metabolic processes, most notably blood glucose and blood lipid metabolism. And to do this, it has to have signaling factors, and we've been working on the signaling factors. The idea being that if we know how insulin signals and through what factors, we can then look at what factors are defective or abnormal, so to speak, in obesity and type 2 diabetes, where the key ingredient, the starting point, is insulin resistance. And we've been able to show that we can reduce insulin resistance by either impairing glucose metabolism in muscle, but we think even it's more common to produce an abnormality in glucose metabolism in liver as a result of increases in dietary carbohydrate or fat intake. And of course, we've been focusing more on the liver these days, thinking that that was the starting point. And indeed, we feel very clear at this point that there's just too much activity of a particular factor that insulin itself actually stimulates, but is also stimulated by food substances which directly activate this factor and lead to not only an increase in its activity, but an increase in its actual production. So the levels of this factor rise in the liver, the activity rises, and we know that this is the starting point for a downregulation of other factors that are important for keeping glucose levels lower and keeping lipid levels lower. So it's basically this work on insulin signaling and insulin resistance that perhaps was the basis for receiving the 2012 Middleton Award. And of course, I'm very grateful to the VA for all the support that they've given me through the years, a place to work and live and pursue what to me is the Holy Grail, trying to understand how we can get diabetes and obesity and how we can cure it. And I think we have factors that can reverse everything. We're developing more factors, and these factors are very effective so far in treating animals. Hopefully we'll get, at some point in my lifetime, to see them used in humans, because we know they work and work well to prevent the whole insulin resistance thing.
Now, I understand that it is possible that diabetes can actually lie dormant in the body, and a traumatic stress upon the body, such as like a car wreck or something to that effect, can weaken the body enough that can actually allow it to wake up, so to speak.
Well,
is that true?
No, not really. It doesn't cause diabetes. It can make diabetes worse.
Right.
Any kind of stress will turn the liver on to make more glucose and lipids. When your stress hormones go up, they turn the liver on to deal with stress. And the way you deal with stress is to make more glucose available. Right. And of course, that's an innate response. No, I think the real cause of diabetes is overnutrition. And that's the stress that the body is being replaced. It's our idea that we all have the machinery, the metabolic, the genetic machinery to respond to overnutrition by making too much of or activating this factor in the liver, which then makes the liver make too much glucose and too much lipid and develop obesity, insulin resistance, glucose intolerance, and ultimately diabetes. And this happens on such a widespread scale, I think it's kind of ludicrous to think that there's a genetic defect. No, we think that we just simply have the apparatus, that all we have to do is eat our so-called Western diet, and we are very much prone to develop obesity and diabetes. I mean, you're talking about a disorder that affects 40–50% of the population over 40 and 50. According to the ADA and the New York Times. So to say that that is due to a genetic deficiency, I don't think so.
That's interesting. Now, I noticed that you have your poster back here, right? Right behind us. Would you mind moving slightly over? I'd like you to actually explain some of it, if you could.
Look at how insulin works in muscle and in the liver. We know the players, and it turns out that one of the players that's important in both tissues is this atypical protein kinase C, which phosphorylates a lot of proteins during insulin action, some of which is quite important to regulate glucose movement into the muscle cell, and also we're finding out more recently it regulates factors that are important for improving the function of mitochondria in muscle. So that's a really good effect of our factor. But in the liver, the factor is necessary to make lipids, but unfortunately it itself is activated by lipids. And it itself, when it's overactive, can downregulate the effects of insulin on another pathway that uses AKT, another protein kinase, to regulate or to suppress glucose production. It turns out when this one factor is overactive, it actually produces more of itself in the human liver, and it then inhibits the activity of AKT, and thereby it leads to an increase in the factors that cause increased glucose production in the liver. And of course that's why you wake up with an elevated blood glucose in type 2 diabetes, because your liver can't be turned off very well. And of course when insulin levels rise, they only actually make the whole situation worse in terms of activating the bad guy, the bad kinase, so to speak, bad in this situation of overnutrition, that is. And of course, with that combined effect of insulin and the lipids activating our factor, and itself activating itself and making more of itself, you're in a vicious cycle. The only way you can stop that cycle is by diet. That'll break the cycle. Or we're developing new compounds. We have one that has high promise. It selectively hits the liver. We don't want it to hit the muscle. Unfortunately, it does not get into muscle. Serendipity is the reason for that. But that phenomena allows us to put that agent into animals, and it can totally prevent the ability of those animals to develop diabetes when we put them on a high-fat diet or a high-carbohydrate diet. And it can largely diminish their obesity and other animals.
That's amazing. And how far away do you see before human trials?
We're ready to go. All I got to do is find somebody who's willing to take the plunge. And of course, we're also going to be developing new compounds. Plus, we don't know for sure that this compound is the one we finally want to use. But the idea is to also develop derivatives, which we can easily do by simple organic chemistry. We can derivatize our compound and try to further increase its tenacity to bind to the target. And we know exactly where it binds on this target through X-ray crystallographic studies. So, we can use computer-based bioinformatics to find things that'll hit our target, that are related to our master molecule, the beginning molecule. We already have several derivatives. We know that they all work as well, actually. But we want to develop more and keep looking for the best magic bullet. We don't know that we have the best one yet, but I think it could easily be a magic bullet.
Well, I do like the idea with the use of the nanocells and the idea of using the spherical, because its surface area is greater than, you know, especially the internal, and if you want to add the idea of delivering the medication to a specific spot and being able to deliver the most possible, a sphere would naturally be the best.
Well, we're not using nanoparticles.
Right.
I wish, you know, it would be nice if we could develop something to specifically put our agent in the liver. Right now we're just giving it systemically, but it just so happens it seems to be largely localized to the liver. We know it doesn't get into the brain, we know it doesn't get into muscle, we are reasonably sure it doesn't get into the islet where insulin is made, and we don't really have any evidence that it gets into any tissue at this point other than liver. It seems to be quite selective.
Well,
and we may not need to have anything, a delivery system.
Right, because you might not have to differentiate so badly because it's so specific.
At this point, it seems that way.
Awesome. Well, I want to thank you very much for your time there, Dr. Parise. Congratulations again on the Milton Award there. And,
thank you.
Keep up the good work. Right. That's all I can say.
Well, we're putting the extra money that the Middleton Award gave us to good use in the research.
Beautiful. Thank you so much for your time. Appreciate you.
Well, I would take this.